All right, so yesterday we stopped right here. Okay, we did a little bit kinematics calculation. So you realize that just for this pure elastic scattering turns out to have the most efficient energy transfer. You'd like to have your hypothetical particle and the target roughly the same order of mass. If they're separated by a large factor, and then you're not winning in terms of the energy transfer. So that's one of the reasons that prompt, I guess now we have a very clear yellow tape. Okay, so in fact this is a Chinese joke. I don't know whether you've seen this this novel, one of the big 4 novels called The Journey to the West. Okay, so it's this monk with with 3 pupils, and one of them is really, really good. He's a monkey, he's a monkey king. And then in order to make sure that this monk was not really attacked by the devils, so he used his stick, and draw a circle. And anybody who entered the circle will, be burned or something like this. Yeah, this is exactly the purpose. Okay, who's the monkey king? All right. Where was I? So the reason prompt we tend to say, okay, why don't people build a detector with all the atoms in there, easy, and just look for these hypothetical particle, which is maybe 100 GeV heavy, and just scatter and transfer its momentum energy to it. Okay, it seems to be a high school thought. But it's actually deeper than this. I'll show you the second thought, important thing that goes into his thought chain. By the way, dark matter could be equally interacting with electrons. You can imagine, right? If the hypothetical particle somehow coupled to the quarks, and it can equally weak interaction, for example, same order coupling to the quarks and to the leptons. And so you imagine that it could be doing the same thing. Now, there's also something that's important to bear in mind. Yesterday afternoon, there was one of the student talk discussing the so-called coherent scattering of the neutrino with nuclears. Now, classically, if you have a wave, okay, and then everybody knows interference, and there is this so-called coherent addition of the amplitude, and you take square to get the overall the intensity. Yes, you'll be surprised to find that in the case of coherent addition, the amplitude of the summed wave, okay, instead of being just having 2 sources here, you're adding amplitude. If you're just adding the intensity from each, you get a factor of 2. However, if you are doing the coherent summation, you add the amplitude up and then take the square, you all of a sudden get a 4, 2 squared to the 4th, okay? And then there could be this constructive or destructive. Okay, and so what's the rule of thumb? Okay, if you have 2 trees here which are very far apart and your wavelength is too short compared to the distance between the 2 trees, you don't get this. So there's some rule of thumb that the wavelength of this is comparable to the characteristic spacing of the sources. Okay, and same thing happened in the quantum wave. So I'm going to hand wave from now because my theory friend will always get very mad at me. They say, okay, the real momentum scale in a scattering problem is not the energy of the incoming particle, but rather it's the momentum transfer. Okay, but let's just bear with me. Okay, assuming that the momentum transfer somehow relates also to the incoming particle's energy, and you can always compute the wavelength of the incoming particles through the wavelengths and momentum conversion, yes? And you can do it for photon, you can do it for electron, you can do it for anything, yes? Happy, yes? H bar, you know what H bar is, or H, Planck constant. And I always remember this number from the PDG, yes? And you can almost also convert based on what you know about optical photons. Optical photons is about electron volts. Why is it 1 electron volts? Because 13.6 is the hydrogen atom's binding energy. And then what's the wavelength of the optical photon? It's about micrometer, okay? And then you can scale up and down according to the incoming energy, okay? Now, let's think about X-ray, okay? Let's think about X-ray. And that was the first experiment, sort of the modern physics experiment I taught my students It's some iron that produce two the lines, which is of the order keV, and they're looking at a crystal of sodium chloride and figuring out what is their interference, and then figure out what is the lattice spacing of the sodium chloride. So what's the wavelength of the X-ray if the X-ray is keV? And the reason of having this pattern of the interference, of diffraction rather, is because of the rule of thumb. What is it? I give you enough hint. I both give you h bar, and I also gave you sort of the optical photon versus its wavelength. You should be able to. It's nanometer-ish, yes. Yes? Simple calculation, okay? And just because of the reason that we always talk about X-ray diffraction on a characteristic spacing, which is angstrom, okay? So that's also easy. By the way, the fundamental interaction of this is electromagnetic, but it doesn't matter whether it could be a strong interaction for that matter. Or the coherent summation has nothing to do, doesn't have to know about the interaction. Okay, so it's just the Schrödinger, is what we call the uncertainty principle, or Schrödinger, Heisenberg principle. Okay, so far so good. And then you would understand that this so-called coherent neutrino scattering is nothing fancy. It's just the weak interaction version of the X-ray diffraction, but with a characteristic spacing, which is now the spacing between nucleon inside the nucleus. Yeah? So assuming that every proton and neutron is of the order Fermi, or 10 to the minus 15. Yes? Why do we do this? This, by the way, the size of the proton and neutron are actually measured. Okay? Dima was commenting what happened to the charge radius. The charge radius of the proton and neutrons were measured to death, okay, very, very accurately. So you know their spacing 10 to the minus 15 or 1 femtometer. And again, taking this 200 MeV times femtometer gives you h bar. And then you know that for a 10 MeV or below neutrino, if you compute the wavelength, that's just about bigger than the size of, it's about 10 femtometer or so. Okay? What does it mean? It means that it's big enough that you don't see individual. So it's just the size that it's bigger, slightly bigger than the size of the spacing of the nucleon. And so you have coherent summation. It turns out that this is weak interaction. So in fact, you can think of this neutrino as changing a z particle with individual proton and neutron, but then you sum up the amplitude to get the total probability. The funny thing about the weak interaction, it's a little bit nerdy, but the electromagnetic interaction is the same thing. The electromagnetic interaction sort of ignores the neutron but sees the proton. And the weak interaction is just the other way around. The Z exchange likes proton a lot less than the neutron. So in this case, if you take the first order approximation, the amplitude or the probability of such a thing happening scale with the neutron number squared. Okay, so a nucleus inside of, so the bigger nucleus, your wings. Okay, so that's the importance of the approximation, not the picture. So I should tell you the dominating sort of thought in 1985 when Wheaton proposed such a method. So at that time, people were thinking, oh, dark matter could be these particles that may exchange just the Z particle. The Z particle with the proton and neutron. And so, man, this whole thing, this whole formalism just ideally just you copy it. Right? If it's a Z exchange, you do it the same thing for the proton and neutron. You end up with the same n square enhancement to the scattering probability. So he proposed that. So that's very important. Now, rather, if you do an experiment with the electron, what's going to happen to the electron? Okay, so first of all, the number of electrons in the atom will scale with the proton number. He said, that's fine. It's a large number of electrons there as well. Now, assuming you make a magic experiment that you can see individual electrons scatter. However, the size of the electron, the characteristic size of an electron in an atom is instead of being the size of the electron, which we don't even know how small it is, but rather it should be the characteristic size of the atom, which is angstrom. And then if you compare the wavelengths of the neutrino hitting on these electrons, you realize that it's looking at individual electrons rather than seeing their coherent enhancement, because your wavelength is too much shorter in comparison to the size of the atom. Okay? So for the electrons, A, you don't get a sufficient momentum transfer, and B, you don't get this coherent enhancement in the scattering probability. Therefore, people were talking about anything that's stemmed through Witten's proposal was using the nucleus as a whole to detect the dark matter interacting with the nucleus. Okay, so that's the at least the theoretical prejudice, also practical reasons. Okay, so far so good. So that's the proposal. Okay, and now you can verify what I'm telling you is true. Okay, so for a typical weak scale dark matter, with a speed of 1,000 of the speed of light, what do you get for its momentum? And then conversely, what do you get for this characteristic wavelength? Thinking.
It's not really 6 or just MeV.
Divided by 1,000, which is just 100 MeV. Yes? Yes?
So 100 MeV?
So it's about 100 MeV. 100 MeV is, sort of a few femton meters, so on and so forth, and so you get this. Okay? In fact, if the dark matter is heavier, this starts to becoming not true. So the distance scale allows you to see individual proton, neutrons. In fact, this is actually a visible effect. Once you start being able to resolve individual proton, neutrons, what's going to happen is that the dark matter, if it strikes on a single proton or neutron, it could make the nucleus to be at the excited states. Okay? Excites additional degree of freedom inside the nucleus. And people are also start trying to come up with a merger, or some fusion between the nuclear physics and particle physics, trying to do a more rigorous calculation. What's going to happen if dark matter just strike a neutron and excite the internal degree of freedom? Nowadays, most of the searches, like experimentalists, are extremely naive, just assuming that whatever, how heavy this dark matter is just kick out the entire nucleus. This is not true. Okay, so in fact, you really need to do the nuclear physics calculation to really figure out what's the final state. But that's aside. Happy? All right, so what's going to happen? So what's going to happen, by the way, so assuming dark matter is 100 GeV, assuming that your nuclear target is also 100 GeV-ish, okay? So the incoming particle converts, roughly speaking, half of the energy to the nucleus. Yesterday we did the calculation, yes? About 100 keV was the initial incoming particle's energy, and then it becomes 50 keV, right, after the recoil. And that's easy enough, by the way. That's easy enough energy to detect. It's not easy for an experiment like Juno or large neutrino detector. But for a smaller detector, this is almost peanuts. Keep going down. When it gets difficult, it's keV-ish. That's another boundary that typical particle detector, you have some issues of being able to detect them while being understand all the background. But 50 keV is peanuts. So how do people do the measurements? This go back to the standard techniques people are using building these different lower energy detectors. Simplest thing you can think of is scintillators. Okay, you just need to make your detection more efficient, putting a lot of photosensors around, and then the second is also old technology called ionization. Yesterday I mentioned to you how that did Chadwick measures neutron's mass. He was using an ionization chamber. Okay, nothing but trying to count the energy converted into ionization after the scatter. Okay, so that's the ionization detector, also very old-fashioned. And third one is more solid state, so to speak, that some of the energy, if it strikes, for example, on a lattice, the nucleus on a lattice, and that one is producing the vibration, thermal vibration energy into the form of phonons. And then phonons is a bit more difficult to measure. And in order to catch its quanta, you have to use very low temperature technique. People use squid, so on and so forth. But this has been developed in the past 40 some years. Okay, particularly I guess people initially when are discussing the recoil of the neutrinos on nucleus, because eventually people want to go all the way to MeV because that's the majority of the nuclear decay neutrinos, and that energy scale. I should actually show it. Could be very low. Now, on this page is nuclear neutrino scattering, and if you take the energy of the neutrino to be 1 MeV, and if you take a nucleus, let's say, which is 100, you'll all of a sudden realize that you have to have a detector which is sensitive to 10 electron volts, and that's not easy. 10 electron volts, not 10 keV, 10 electron volts. And so people in 80s are thinking about these detectors catching the coherent neutrino nuclear scattering. They always want to push the threshold down to 10 electron volts-ish. And most effective one of people thought at that time was to make a phonon detector and using the auto-solid state techniques. And interestingly, what happened was that technique was fancy, was nice to see some of the excitations, but solid state is a dirty business that you see this energy, but you also see a lot of noise at that energy. And secondly, because you're using all the liquid helium temperature, so on and so forth, the detector was difficult to get scale up. So they all stay with few grams of the detector, not being able to scale up. And so what's interesting is that about, I'd say 20 years ago, at that time, people were sort of democratic, working on different detectors. But about 20 years ago, people realized that just a simple and stupid scintillator detector will be very inefficient doing that because of the limited ability to make good position reconstruction, because you're just a monolithic detector with limited position reconstruction capability. It turns out at that time, this detector turns out to be running out of steam in terms of scaling up. And then one technique, which is a combination of using the scintillation as well as the ionization, combining them, specifically using noble gas, liquid noble gas, showed its potential being able to scale up, while being able to have a lot of control of where your background coming from, so on and so forth. And now, up to today, I think that it's the dominating, it's the most cutting-edge experiment after 20 years. Okay, so I'll show you one interesting picture that this was right before I joined this game of doing dark matter. So this was a plot made by a rather small, in today's standard, liquid xenon detector. Okay, and so in comparison, a CDMS was using what I told you about the very cold silicon, very cold germanium, trying to detect both the ionization and the phonon, developed for years. Used to be the leading experiment, and Xenon had sort of just made their first upgrade, their first data of their first grade upgrade. And you all of a sudden see, oh wow, just with, I believe it's like a 15-day of running or something. And being able to get, by the way, this is exclusion. I'll explain what does the exclusion mean. But the y-axis here is the cross-section of this hypothetical particle scattered with any nucleon, okay, inside the nucleus. And the x-axis is the log scale of the dark matter. And you see that around here, where is 100 GeV, which is the dominating theoretical prediction, it's getting to sort of seeing the window of the discovery, just with 10 days of data. And you see people at that time has the SUSY contours that was so aggressive, saying that if you push this down by 1 order of magnitude, you cover most of the parameter space. And a lot of people get super excited, not because you get here, just because just one little step, maybe 5 years, you'll be able to catch this, okay? Unfortunately, nowadays, people's mind have been switching a little bit after all the effort I will be discussing. Okay, so what about these noble gas detectors? In fact, you could make all noble gas into detectors. Helium is a nice detector, krypton is a detector, blah, 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 everything, okay, can be made out of detector just because in principle, you can make it a tank of liquid at some temperature and just look at what does the photon being produced inside, deeply inside this liquid, as well as ionization, particularly because these noble gas atoms are so happy, they all have full shells, so any ionization being produced by a recoil, if you apply a tiny electrical field, you can drift it all the way from deep inside to the surface, and then you try to find another way of detecting it. So that's the beauty for making this detector, just a tank of liquid, and being able to see both the scintillation as well as the ionization. I will discuss mostly about xenon, but using argon, it's mostly very, very closely the same principle. Xenon is also easy to liquefy at negative 100 Celsius. It doesn't need super fancy cryogenics to do this. The density is high. It's about 3 of the water, so it's good. The only downside is that there's about, I think, 0.01 ppm, 10 to the minus 8 of the xenon just naturally in the atmosphere. So it's low, but if you collect all the atmosphere, it's infinite. But still, the world production every year is not a super big number. Right now it's about 100. 10 years ago, it's about 50 tons per year. And so if you're building a detector bigger, you're competing with the world market. And it could be up and downs because of this, okay? Depending on who's competing with you. All right, so one word now about the detection. Does the animation works? Beautiful. So the animation also works. Let me just describe the animation, and then I will go a little bit into the physics. So let's rewind. So what happens is that you have an incoming particle, whatever it is. So it could be a gamma ray, it could be a dark matter, okay? It's coming in, and imagine that you have an atom here. Simplistically, you get some excitation which converts into photon, and then at the same time, it also has sufficient energy to ionize some electrons. So you collect these electrons, so you see the first splash of light because of scintillation. And how do you do with the electron? It turns out to be a simpler method that you drift all these electrons from the liquid to the gas. And because the gas molecule spacing, or rather atom spacing is larger, if you apply a stronger electrical field, the mean free path in between each atoms becomes larger. You use E multiplied by this mean free path, it's more sufficient to ionize more of these atoms, and that gives you an amplification. You get an amplification of the ionization as well as the scintillation. And then basically, every electron ends up to have a well-defined number of photons, which is secondary, and you collect these secondary photons. And from that, you compute how many of the initial ionized electron you have. So it's a very simple method. The key beauty is that then you only have one set of sensors. You can cover both channels. You just put the detector top and bottom. If you have money, you can even put it on the side of all these photosensors, and you catch both lights. You get both the scintillation and ionization. And it turns out there's advantage of doing so. You can actually not only get the energy deposition very accurately, and by combining both channels, you also can get a very good position resolution because the secondary ionization light happens very close to your top detector channel, top array, and where that happens, you actually are almost taking a picture of the event that happened on the X and Y plane. And by counting the difference, or by measuring the difference, time difference between the scintillation photon and the delayed ionization photon, you also know how deep this happens. So you get an X, Y, and Z reconstruction this way, up to millimeter, sub-centimeter level for sure. Very, very robust. And so you get the position, you get the energy, and also for some more subtle reasons, being able to see both scintillation and ionization allows you to do some particle ID. And this is understandable because different particle has different ability to make ionization, okay? Because ionization depends on the charge deposition density. So on and so forth. So it has these multiple advantages. Also, if you have something, for example, gamma ray scattered 2 times, which makes two energy deposition, because the two energy deposition happen at different location in the detector. And then although the scintillation photon might occur to be a single scintillation photon light, but the secondary ionization signal will be differed, okay, depending on how many times scattered. So by counting the so-called ionization light we call S2, you will also be able to see whether this dark matter particle, which is single scatter, versus the other background particle, like neutrons, like gamma rays. Okay, so there's multiple things. Now let me explain one important piece of physics, which is troubling if you think a little bit further about the scintillation process in the liquid xenon. Now, people who work on Juno knows that the initial scintillation photon in Juno is using this fancy liquid called LEB. It's UV photons. And the actual photons that being detected by the photosensor rather are not the initial scintillation photons, but being absorbed, but then re-emitted as the blue photons in a very short distance, roughly speaking, 10 centimeter or even less, okay? So such kind of scatter-rescatter process happen all the time. Now, if you look up the atomic database and try to see what are the primary photons that say, for all the noble gas, going from its first excited state to the ground state, and that level determining the wavelengths of the photon, you realize that all these noble gas, there's no exception, all happen at far UV, okay, 100 nanometer, something around that thing, okay? That's fine. Now, the even troubling fact is the following, okay? Imagine you have 100 nanometer primary photon being generated by some energy deposition, okay? And you look up what is the absorption probability for this photon to be absorbed by a nearby atom. And you do the computation. The cross-section is something of the order 10 to the minus 18 centimeters squared. Probably doesn't mean anything to you. But if you convert that number into just how thick this particle has to travel before being absorbed, you find it's like less than millimeter, okay? So all photons created by this transition from the first excited state to the ground state will get immediately absorbed. And then essentially this creation, emission, all these processes will really smear out your ability to actually see these photons, okay? So that's very bad. So what's the magic? What's the magic for xenon, argon, and detection? Why we can still use it as a scintillation detector? Pure. We don't need, actually, we don't have any wavelength shifter. You don't add any stuff in there. It's bad. You don't want to add any wavelength shifter inside the liquid xenon because a lot of them are electronegative, so it will hinder your ability to be able to drift the electrons, okay? So what happens is the following magic, that I'm only talking about excitation. If some energy deposition excite one of the xenon atoms, okay, or krypton atoms, or argon atoms, it turns out that instead of re-emitting this excitation into quanta, what it like to do is to form a van der Waals bond with a nearby atom, which is at its ground state. And then it's forming a so-called excimer, a two atom, quote-unquote, short-lived molecule, very short-lived inside the liquid. Okay, so although it's majority monoatomic states, but then once you get a little excitation, you can form a very short-lived molecule. And that molecule de-excites, emitting a photon wavelength which is unhappy to all the single molecules or single atoms around it because the energy level has been shifted. And just because of that reason, you can create the scintillation, and these photons get no absorption and travel a long distance in the liquid before you catch them. Okay, so this happens in all noble gas. And just because of that reason, if you look at also the database for the atomic excitation, de-excitation, you realize that time scale is very short. But if you look up, for example, argon, de-excitation normally has two time constants. One, it could be as long as microsecond. The reason is the same thing. The de-excitation for this diatomic short-lived molecule does have a long lifetime. And by that, liquid argon is claimed to have this very nice power shape discrimination to some particles. Okay, so that's one piece of interesting physics about these liquid xenon scintillation. Happy so far? Good. All right, so yesterday we also have talk on GVD. Everybody knows about photosensors. We're not using, in this experiment, 20-inch or 10-inch, whatever. So this experiment, because the size, even a ton of xenon, it's only 300 liter, okay? A ton of xenon. Therefore, the photosensor we use is, it has to be UV. By the way, the photons that I was mentioning, the de-excitation of the excimer is about 178 nanometer. And so it's a special sensor that has to be, both the window has to be, transparent to the UV, as well as the photocathode. So, we have been using throughout the history 3 types of scintillation photosensors. This is a square photosensor, 1 inch, and the round-headed one, 3 inch. And in the newer generation, we're going to use this 2-inch photosensors, very, very flat, and with 4 independent channels. In the newer generation of the experiment, you pile it up at like an array like this. We think that this is actually a nice combination that we get both small pixelized to get very good position reconstruction ability, as at the same time it's not as many channels as, for example, silicon PM, some things like this. And these are beautiful, beautiful dark grade under 100, negative 100 Celsius. A big sensor like this, we managed to get something like 10 per second dark rate, okay? So that allows us to push the energy threshold really down. All right, so very quickly on one of the experiment with the xenon, which I work on. This is at the China Jinping Underground Lab. Just to give you a sort of, this is a terrain map. This is Shanghai, and this is Beijing. This entire province is called Sichuan, a lot of mountains. This is the Tibet Plateau. So it's sort of in between, sort of flat, going into the plateau. There's a lot of mountains. And so one of the river, the sub-branch of Yangtze River called the Yalong River, run through a mountain. And so this mountain, in order to develop the hydropower of this river, the company who does all the development dug in a 17-kilometer deep tunnel through it by 2008. And so it was a free tunnel. And at that time, the Chinese physicists are talking about somewhere finding a underground lab. In fact, Chang'an was one of the initial people. And also Hong Bo-hu from IHAB, they were looking around all potential sites. And this was mentioned. But eventually it was this company and Tsinghua University signed a very good MOU. So the company said, oh, you guys come, we will donate an experimental hall at the center of this tunnel, which is very deep, and then just get the physicists to come and do the experiment. So that was very fast and cheap development for us. And then 4 or 5 years later, after that initial period, the water dam that's blocking the river to make electricity was completed. And before the worker went away, they started asking us to, what do you want to do 10 years from now? Okay, and it's like right 1 month before the worker go away, they say we want to do some more excavation, but you have to let us know what do we want to do. It's like within 1 month. And so we were scrambled to really figure out what is the right optimal size we wanted. But eventually, everybody, we just did, kind of. It's like figuring things out from your butt. It's nothing fancy. We just said, oh, we want a bigger hall, things like this. And this became a reality 2016. That these workers who before they went away make further excavations into 8 experimental halls at slightly different place, but they're still at the center part of this tunnel. So all experiments that's going to happen later on will be situated in the second stage of the CJPL. Right now, Panda X I work on has been occupying this location for more than 4 years. And there's another experiment, nuclear astrophysics experiment, also have been using this place. But everybody else was starting to moving in. All right. Okay, so how much I want to say about this? So we built this liquid xenon detector in 3 different stages. The reason is also obvious, that I believe 15 years ago we thought after 1 ton of liquid xenon detector we will be done. The rest we will hand it to the accelerators, just because we thought Susie was correct. And then with the 1 ton detector running 3 years, we nail what dark matter is. At least we know the mass. We know the kind of the interaction with the nucleon, and then in order to start its spin and so on and so forth, it's really up to LHC. And so the initial plan was that we go with 2 stages. The first stage has 100 kilograms just to get things started. The second stage has 10. And we thought that would be the ultimate generation. And now we are in the 3rd generation now, containing a 4 ton, roughly speaking, 4 ton liquid xenon in the detector. We still haven't seen anything yet. And there are two competing projects, one in the US, one in the Europe. The scale is similar. The US project called LZ has 7 ton of liquid xenon. And Europe is slightly smaller, called xenon N ton. So in combination of all 3, nobody has seen a convincing signal yet. That's why the sensitivity of the experiment has been pushed tremendously by almost 4 orders of magnitude from day 1, 15 years ago, but still no signal yet. By the way, no signal, the simplest thing of interpreting what no signal is that the initial idea, what Witten had, it wasn't Witten's idea, but the Z exchange, exchanging through the standard model weak interaction for this unknown matter with the nucleus. That theory is gone. Unless you do some tuning saying that the dark matter coupling to the Z is super, super small. You can always evade such bound, but it becomes a little artificial. Okay, so our collaboration is about 100 people. These are just showing some pictures. The real detector is actually sitting inside now. The 3rd generation of the experiment is sitting inside the ultra pure water tank. So this is viewing everything from the top. The center part of the detector it's not super big, right? As mentioned. So for a 4 ton xenon, it's about 1 cubic meter. So it's a rather handleable size. This is, by the way, you can see the photosensors. This is the bottom photosensors. And then we have the cryogenics over here, so on and so forth. So it's quite some effort of building the experiment. We started 2018, and in the middle we had the COVID. The infrastructure of the lab has been coming online very slow. So my university decided to pump in money to try to pay for all the stuff that we were building, just to speed things up. And it's, I'd say money well spent. Okay, okay, wrong way. Okay, let me keep going. Now, just the one thing about the difficulty. Okay. People talk about background all the time. Sounds like something that's important for all these low background experiments, but it's also a boring thing to remove them because it's just so hard. Okay, most of the background coming from the cosmological generated background has been totally eliminated by the steep depth of 2,400 meters. So the hardest core of the experiment is trying to remove all the other things. Now, all these noble detectors, noble liquid detector, particularly for xenon, you could also more or less ignore the background coming from the detector materials. Okay, anything related to the wall, to the photosensors. The reason is the following: with a 3 times denser density than the liquid, the stopping power for gamma rays is actually quite nice. And what happens is that all these peripheral events will happen really at the peripheral. And now, this is not sufficient. If you have a liquid scintillator detector or just using a liquid xenon detector with scintillation only, people thought about it because it's simple, it's symmetric, it's beautiful. But those detectors, turns out, will have a problem that you may have maybe 1 out of 1,000 of the time that you get a misreconstruction in the position. And those misreconstruction of your position is already sufficient to give you a leakage of the background. And the beauty of these so-called two-phase detector, where you detect both the scintillation and the ionization, is that you get a very accurate position reconstruction, that you don't make a mistake that way. And also for the reason that because you detect both scintillation and ionization, you can actually distinguish between the particle that you really like to catch, namely the dark matter scatter with the nucleus, rather than the gamma rays. You can do the separation this way, because just the gamma ray has different ionization power in comparison to a nuclear carrying certain energy. Okay, so it turns out that most of the boring backgrounds from radioactivity from the wall are shielded with, you just make a visualization, and that's can be trivially removed, or trivial in the sense that you don't want it to be super high. You need to be careful when building the detector, but that's mostly it. It turns out that the most risky background came from those radioactive gases that can get solved in the liquid, and they go everywhere. They go everywhere. You cannot really do fiducialization. What we have been fighting with generation after this generation of experiments was we see a krypton isotope, which is radioactive, krypton-85. We observe argon-39 came also from the argon-40, losing one neutron, which is radioactive. We've seen radon-220, 224, all noble gas, all these little things. And the level we are talking about is that inside each kilogram of xenon, we are talking about seeing a few of these atoms. That's the level. Then you can start seeing them. The last one, which was not noble, not inert, but active. It's trace amount of tritium that we saw in the detector, and tritium has 14 years of decay life. And we're also talking about something of the order of a few per kilogram. And those are already sufficient to become the dominating background in the detector. So that's just the level how hard these things are. So I tell you one story about these tritium background we saw in the third generation. We don't know precisely where they came from, but there was good suspicion that we were using tritium as a calibration source by loading them into detector, because the energy window, it's uniformly distributed. The energy is about few tens of 10 keV-ish. It covers the right energy window. And because it's active, we thought that using the standard technique that we remove nitrogen and oxygen, we could also remove these tritiums. But it turns out that techniques was sufficient at some level, but then becomes insufficient. There are some level of the tritium that you just cannot remove with the traditional method. We think that inside the detector, some dead corners that once we circulate, taking the liquid out, they're also always trapped in there. And then they still have the thermal motion that's being able to move into the detector, so on and so forth. And there could be also being attached on the surface, and then you cannot really remove by liquid purification. In any case, this level of tritium you see nicely, a very nice tritium peak in the detector. It's probably the most sensitive tritium detector in the world, by the way, because when we talk about the environmental health people who are doing the water tritium level measurement, and their level dealing with billions times higher than us. But even that level, you just drink it right away, right? So they have no idea. Environmental science people have no idea how to remove this trace amount of the tritium. What do you find something which is chemically more likable to tritium that you can try to grab it chemically? They haven't been able to teach us. So we were using a more stupid method, trying to distill them based on the fact that any chemical form of tritium likely are having a lighter than xenon. Therefore, you have different boiling point, and we try to solve them physically by using cryogenic distillation. This was effective, but not super effective. We did this one round of distillation, managed to get things by a factor of 10 also. But once you get it to a factor of 10 also, by the way, it's getting harder and harder to measure it, right? So imagine this peak is reduced by a factor of 10, and then it becomes, how well you know your energy model, how know you know all the other background. In fact, it's also an interesting thing that all the other background I was talking about, the krypton, radon, they are all beta decay. It turns out that these beta spectrum, these beta energy spectrum at a very low energy, these nuclear physicists cannot produce a convincing or very good prediction of what their shape is. There's this little atomic effects when a beta decay electron can change with atomic electron and so on and so forth. And that could change the spectrum, but nobody can come up with a very robust nuclear physics prediction of the beta spectrum to start with. So it's tricky, once you get to that level, both your background level and the shape becomes a bit shaky. But we do it anyway, okay? We do it anyway for the reason that we have particle ID, okay? So all these scattered with the electron by gammas or by betas are all hitting electrons, okay? And we care is the dark matter hitting with the nucleus. And because there are ways of different ability to make ionization, typically on this graph, the y-axis you just treat of the level of the ionization. The more, it's more electron-like. The less, it's more nuclear-like. Okay? So typically we draw a line and just try to count the number of candidates. Of course, the real analysis we did, that fancy likelihood fit, taking into account the entire distribution. You know the distribution by using calibration. You try to figure out what is the electron recoil distribution, and you use neutrons to hit the xenon atoms and try to produce nuclear recoils. By the way, in one of my exercises, I ask you also to compute a typical neutron when you interact with xenon, what is the recoil energy. It turns out to be the right ballpark. That's actually a very ideal calibrator to simulate what happens when a dark matter impinge on a nucleus. Okay, so you do that and you do the fit. By the way, we always open box, get excited about the number of candidates there. The question to ask is how much your background is there. For this particular data sets, okay, if you just do a simple cut and count measurement, we saw 6 events in the signal region, but then we expected 9 background per experiment. So it was actually a downward fluctuation of the background. Unlucky or lucky, depending on your point of view, when you have a downward fluctuation background, in fact, your limit gets stronger. But that's not what we want. We actually want to see a signal. Okay, so now let me move on to discuss just one point about seeing nothing. Okay, so you say, okay, all these efforts you see nothing. What does it mean? Okay, it turns out that a lot of these rare search experiments, eventually you cannot claim a signal. You have to then say, I'm going to set some exclusion or upper limit on some interaction strengths. Okay. Now, first of all, what's the point of seeing 0? Everybody knows Poisson distribution, yes? Poisson distribution, that you start doing number counting, this number, say, I wait for X days, I see 9 events, or I'm expecting to see 9 events, but if you do 1,000 of these experiments, you're expecting to see a distribution, right? Around 9 events, there's some distribution. Now, just to take, let's say, mean value 2.3, okay? I'll explain why I picked 2.3. Assuming you have a mean value of 2.3, you do 1,000 experiments, you realize that you have 10% of probability of seeing nothing. Okay? What does it mean? That means 0 somehow maybe have a 10% probability of happening if your mean value is 2.3. And 10% is a magic number that we like to say, okay, you have 90%, people say 90% confidence level of exclusion. That means, okay, you try to figure out what is the probability, a small probability. That's a small probability that your actual interaction strength shouldn't be higher than certain value, because otherwise you're supposed to see the signal already. Okay? So if the mean value is 2.3, you still have 10%. Therefore, if you observe 0, and if you're not counting any background, a typical way of setting your confidence level is that your signal shouldn't be larger than 2.3. And you set your 90%. This is a 90% liquid now, guys. 90% liquid right as your exclusion boundary. Okay, makes sense? So that's what we do. If your signal strength is 2.3 events out of 100 days, you recompute into some physical parameter. For example, cross-section, for example, coupling constant. And such a thing has been done in all kinds of practice of searches at LHC, all the underground labs. It's typical There are fancy statistical terms, but that's the basic idea. Okay? Happy? All right. And so here is what you see, turning the absence of dark matter into a limit, like I mentioned. It's just to give you a context of what I mean here, okay? For comparison, at least the dominating SUSY prediction is in between 10 to the minus 43 and 10 to the minus 44 centimeters squared for the interaction with the nucleon in 2010. And, And theorists are also fast pacing. Whenever we have a more stringent exclusion, they come up with a different, more harder and harder prediction. Anyway, if you see where we are now, we are, the prediction was here, okay? We are here, okay? So unless you really fine-tune the coupling constant, so on and so forth, it becomes highly unlikely that some of the predominant models in early times was either bogus, they were super aggressive, or it was just the model was incorrect. We don't know. Okay, now let me just try to make some connection with neutrinos. The highest, almost the highest energy solar neutrino is the famous boron 8 neutrino. Okay, so HEP is even further, but smaller flux. And this neutrino has been caught by Ray Davis, by the gallium experiment in Baksan, and then later on by Snow, by Super K, so on and so forth. Okay, but imagine that you want to have some experiment to catch these boron neutrino, but with a miniature detector somehow. Look at all these detectors. Super K, even Snow is a 13-meter detector with about 1,000 tons or 2,000 tons of the liquid in there, right? And so imagine, this is Juno, by the way. Juno wants to do solar neutrino. I don't know whether we're going to succeed, okay? It's tough because solar neutrino scattered with electron inside the liquid produce an energy deposition, which is sort of, there's no coincidence. You have seeing a single scatter one by one, and then you have to really push down your background level. So we don't know whether we can do this or not. In any case, so there's many of these large detectors still going after solar neutrino, because once we understand neutrino oscillates, and then you can turn the question around. Given neutrino as a messenger, maybe you can learn a bit about what happens inside the sun. Maybe there's some models that produce different solar boron 8 neutrino flux, so on and so forth. Now, just to give you a propaganda that with this little detector we have with only 4 tons, but just because of this coherence effect that I was mentioning earlier, we were able to see about in a year, less than a year, 1 ton year exposure, we were able to see about 75 of these neutrino events with larger uncertainties. So we have a confidence level which is roughly 2.6 sigma. But you see that the measurement is consistent with the solar prediction. And so these things are there, and the coherent neutrino scattering is there. Physics do work. Using this technique, you see that the potential is that you can get better solar neutrino measurements through this very, very unique channel. Okay? So that actually made into last year's some highlights. Let me keep going. We were competing with xenon, blah, blah, blah. Okay, so let me speed up. I'm having very limited time. So the next generation of the experiment of Panda X is that we want to keep going with the avenue that the same detector can do both dark matter, neutrino, and we also have the ability to do good measurements on the double beta decay, neutrinoless double beta decay. So it's a combination of many physics topics in a single detector. We also want to stage this. It's going to be a somewhat new design of the whole detector. We're also going to have a cryogenic liquid scintillator veto in order to be able to get some of the events that's producing gamma rays inside and multiple scatter, and second deposition outside, try to veto them. This turns out to be very important for the double beta decay part of the physics, where the energy range is pushed to MeV, and there is much more dirtier because you're much closer to the original photon energy produced by radioactivities. So let me just skip. This is ongoing, by the way. So we're going to stage it into 2 stages, 20 ton and eventually to 40 ton. And with 40 ton running for 4 years, 5 years or so, you can get to sort of a region where most of so-called WIMP prediction will be more or less covered. It's not going to be 100%, but predominant wind prediction will be all covered by this detector. We'll see. But 20-ton is a reality. We're going to try to upgrade next year. And starting on 2027, we will run with a 20-ton detector. And that's probably going to be the most advanced detector in the world. Just to show you that with this 200-ton-year exposure, we'll get from here by another 2 orders of magnitude, covering most of the electro, anything related to the electroweak symmetry breaking, mostly will be covered by this experiment. All right, so in the remaining time, I just want to give you some flavor of other means of these dark matter detection. For the WIMPs, not only we can search them underground, because it's a full model that has predictions both on the scattering as well as on the annihilation, and the creation. It's a fully testable model that you can try to do, looking for the annihilation signal in the space, as well as trying to create them in the colliders. So indirect detection, in fact, is named after looking for at the center of the galaxy where there's large density of these dark matter, and they could go together and make something that doesn't really, it happens in the early universe until the freeze out, right? That's such a process I mentioned did happen in the early universe, but once the spacing between the dark matter is so large, not able to compete with the Hubble expansion, they sort of disappear. But at the center of the galaxy, this is still happening, okay? And so you try to look for some higher energetic particle, known particles being generated at the center of the galaxy. You sort of reproduce what happens at the early time of the Big Bang. So this turns out to be a nicer way of really kissing with the early universe. However, the problem is that the secondary particles have many origins. You could explain it from dark matter annihilation, but you could also explain it from something else. So that makes the business tricky. Okay. So you could look for final states, for example, the gamma rays, antimatter. Antimatter is nice because dark matter annihilating the parent antimatter. Matters are dominating, right? But the antimatter, for sure, the background should be small, okay, in principle, and looking for antimatter, and then you could also look for energetic neutrinos. The energy of the neutrino carry the info of the dark matter mass. Okay, that's fine. So there are many proposals, ongoing experiments. Let me just show you. But the problem, let me just again stress that it's a hard business. Okay, so the cosmic ray propagation uncertainty will limit your ability to predict the background, hadronic interaction, astrophysical sources, dark matter distribution, and many of these systematic uncertainty has to be taken care of. But it's a large business. People are trying to tackle the dark matter problem this way. One of the most famous so-called access was from the AMS-02, trying to look for antimatter. So they were looking for anti-proton, anti-electron, and this was a pretty shocking access if you compare with sort of their naive prediction of the background. So right now, I think that this has been so accurate that people have been settled that yes, there needs to be additional terms to account for access at this 100 GeV and above energy. But whether the source term is really caused by the dark matter annihilation or some pulsars creating gamma ray, converting into E plus C minus that way, is still unsettled. A lot of the astrophysicists tell me that it's actually the latter explanation may be more viable, because if you interpret this into a dark matter, the signal turns out to be too large as the dark matter prediction. But the jury is still out. There's also anti-proton channels. People are trying to look for signals that way. But it's a hard game. All right, so just to give you a snapshot, what are the field in the indirect detection? So what people plot, okay, instead of directly plotting the sigma, which is the cross section, they multiply by the velocity. Velocity is the factor that went into the flux calculation I had yesterday when you have a beam experiment. So when you have things colliding, you have sigma multiplied by v, okay? And then if you just want to have the sigma multiplied by v value magically fits the relic density that we see in the entire universe, okay? It turns out to be very well defined. It's a very accurate prediction. Whichever mass you have, it should generate a well-defined value, sigma times v, 3 times 10 to the minus 26 centimeter cube per second, okay? So a lot of these experiments are doing measurements at 100 GeV also. So for heavier dark matter, which is heavier than 100 GeV, a lot of these current generation of experiments are running out of steam. Okay, there's not sufficient energy, enough energy coverage, so mass coverage. They're the same, okay, to cover this line over here. So that's what we are going after. So we need bigger detectors, so that's catching more energies. But also, there needs to be better detectors viewing the galactic center, particularly for gamma rays, for example. You do want to have a very diagonal view of the galactic center if the dark matter somehow end up to be a final state, which is high energy gamma rays. So let me show you, there's this upcoming CTA, as well as a proposal, I guess, in the South America called SWAGO, trying to close this window. And also, neutrino telescopes is going to be important to really cover the so-called WIMP annihilate eventually into the neutrino window. And look at what we are having now in comparison to this vanilla relic density prediction. There's a big hole, you know, in this region, particularly if you figure out the dark matter is, let's say, between 100 to 10 TeV or so. Very little experiment can say anything over here with neutrinos. So next generation GVD, Chem3Net, the South China Sea project upgraded. I guess IceCube we have limited because it's not viewing the center of the galaxy because it's not rotating. But we'll also have very important say about this, okay? So that will be exciting, okay? So these are the current running neutrino telescope or proposing you've seen yesterday in the talk. Okay, so very quickly about the collider search, okay? A lot of the WIMP study have been assuming that WIMP itself is heavy. This new particle which carry the information is also, carry the interaction is also heavy. So you can contract it into a point-like interaction. Okay? You don't have to worry. It's almost like a Fermi constant that you don't care W and Z in the beta decay. Similar thing happened there. However, this doesn't have to be true. The dark matter doesn't really have to be heavy if you go out of the WIMP paradigm, and the mass of the mediator can also be small. So nowadays, people are drifting towards a more sort of general description that it could be this new kind of particle with an interaction carrier, which is also light. And then all of a sudden, you have more degree of freedom to play with things like this. This is normally called so-called dark sector, okay, if you heard of the term. It means that it goes out of the standard point-like interaction. I also throw away the prejudice that the particle has to be heavy, okay? Light. So therefore, you can have a mediator of a strength, and over here, there's a standard model strength, and then you play with all these things. But once you have all these, the phenomenology on collider all of a sudden get richer, because you can also directly search for mediator, okay? And mediator, in principle, is also an unnoticeable particle. But then you look for the signature this way. Okay, for example, in the simplest case, when the quark and quark make scattering, assuming that it couples to this mediator, and this mediator then can create a pair of these dark matter particle, you could just search for something with, with a large missing energy, okay, in your colliding events. A lot of times, such a missing energy is hard to search for, so they add a tag into the search requirement. For example, they require that the initial particle maybe radiate out a photon, and then that's going to be a trigger. Oh, hey, look for this event. And for this event, there could be some missing energy due to the final state invisibility. Okay, so this is sort of a standard visible way, a standard way of collider searching for WIMPs. This is not the only way, by the way, but it's just a sort of a more generic way that you use the tag to look for trigger events with a large missing energy. There's a lot of alternative approaches, even at, you don't have a collider beam. You could look for some invisible particle being radiated out into a beam, and by that you search for signatures of missing, this invisible particle converting into a pair of dark matter. For example, suppose you are using an electron beam that is able to count individual electrons, and some of these electrons Bremsstrahlung, right, making a photon, or it can create a so-called dark photon, which is something that's seriously invented, has a U-1 symmetry, and then by doing that, apparently this dark mediator carries away energy. And suppose you know the incoming electron energy, event by event, it's able to tell you how many of these electrons, after a billion of these electrons, how many of them have been radiated into some dark photon, and then you catch them one by one. So it's a beautiful example, but it's a hard experiment too, because there's a lot of standard model background that couldn't produce similar type of losses. Okay. Anyway, let me keep going. So these are two sort of avenues that on the WIMP detection. I also want to speed up and just tell you a little bit about another very sort of theoretically well-motivated dark matter model instead of WIMPs. These are a hypothetical particle connecting to another deep mystery in the standard model, namely that if you look at the strong interaction, it turns out there seems to be no good reason that the strong interaction is CP conserving. We haven't been finding the strong interaction is CP violating. Or rather, if you assume CPT, it's time reversal invariant in the strong interaction. And the way you think about it is that if you just think of the simplest picture that a proton and neutron is made out of 3 quarks, yes, and then up, down, down is the neutron, and then you try to measure are these up, down, down quarks are staying on the same line. If they do, then when you measure the so-called electrical dipole moment, you end up to be sort of very, very tiny. But if you turn out to be not aligned, just think of this way. The neutron has 2D quarks, and then assuming that there's a little tilted angle, they're not lining up in the same line, and then you should actually observe a tiny electrical dipole moment. It turns out that this value of the angle has been measured to be too small, so small to the point of a ridiculous amount, 10 to the minus 15 or 16, okay, amount of the small angle, which means somehow, no matter what you do with the quantum chromodynamics, all the vacuum fluctuations, blah, 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 somehow, idealistically, you still have 3 quarks lining up on the same line for some reason, okay? And the QCD didn't like this, right, because the fluctuations in principle should produce a much larger variation. So this is, on a picture, this is sort of the famous theta parameter problem. Theta is this angle that I was talking about, very much constrained by the measurement of the neutron EDM, and has been a problem 50 years ago, okay? Many, many, many years ago, and people have been finding a way, inventing ways of solving this. And I will not go into how do people solve it, but rather it was the Welchik and Weinberg proposed that theta doesn't really have to be a parameter. It can be a field. Right? Upgraded the theta term into a field, almost like Higgs field, Okay, it's everywhere, and it has this value x, y, z, as well as t. Okay, it's a time evolving field, and it also has its quanta called a particle coming from this field called excitation of this field called Axion. And somehow by doing that, you can solve the so-called theta problem, make a remedy to the reason why the strong interaction is not observing CP violations because of this Axion field and the Axion. So the prediction is that such a particle has to exist. Okay? But later on, a few years later, so they proposed such a thing. I should also mention the Patrick and Quinn was initially who thought about this so-called U1 symmetry, which was broken. Initially talking about this theta vacuum. Then a few years later, people have thinking about the consequence of this particle. Maybe it's a new particle, it's good to have. But at the same time, people start thinking about this cosmological constants, a consequence of this particle. What would it happen? It turns out that this particle could start from some very large value at the initial beginning of the universe, but then the evolution of this field, okay, can be time dependent. It turns out that it was high at the initial condition, and it's almost independent of the initial condition. But during the evolution of the universe, it can relax into some value which is very, very small. And it turns out that the later part of the evolution of this field also dictates the mass of this particle. Okay, so this particle has mass. It can also be the 100%. It's almost like the wind paradigm that you produce something in the early universe and it relax according to this interaction strength to a level which is nowadays, and it's sufficient enough to already produce the visible dark matter. So that was at least the paradigm that, similar to the wind paradigm, that Axion can also be this quote-unquote natural solution for the cosmological dark matter. Let me go the other way. Okay, so such a hypothetical particle can have known interactions, although small, known interaction with the standard model. For example, with gluons for sure, because that was initially predicted to be able to make remedies to the fact of the strong interaction has no violation of the T violation. And so it interacts with gluons, but it's very difficult to observe such a signature. It could interact with the quarks for sure, 2 gluons. And then it could also interact with the photons. Most of the leading experimental efforts are looking for predicted coupling with the photons. By the way, so these predictions came from the fact that it has to solve the strong CP problem to start with. Okay, it doesn't have to be dark matter, but this particle has to solve the strong CP problem to start with. So people have been doing laboratory research for such a field interacting with the photons in the laboratory in all kinds of form. So I'll show you very, very quickly what are we right now. Typically, it turns out this model is also nice, that the coupling constant of this hypothetical particle with photon inversely scale with its mass. So mostly, okay, more or less that's the inverse scale law. And therefore, the visible or the possible constraints is this diagonal line. Okay, there's some wiggle, there's some bands width of it. That's a detail, but it's predicted to live on this line. Okay, it's predicted over there. Let me see. So there's some upper limit. Okay, there's some upper limit, and also some constraint from the cosmological lifetime if you wanted to be a dark matter. On the other hand, suppose such a particle. By the way, it's a boson particle. It's a pseudoscalar. Suppose this particle doesn't have to solve the strong CP problem. Okay, it's just a pseudoscalar particle. And then you don't have to search along this line. It can be everywhere. Okay, it can be everywhere. So assuming that some mechanism created this pseudoscalar particle early on and it becomes the dark matter, in principle, you can search everywhere here. Now, but the best place to search for, if you really want to get 2 Nobel Prizes in one shot, is to search on this line. Yes, and it turns out that people do cosmology, assuming this breaking of the U1 symmetry happens after the inflation. Assuming this is the case, then there's some prediction that the mass of this particle is microelectron volts to millielectron volts range. Okay, so therefore, to solve 2 problems in one shot, mostly people are looking here. Right now, experiments trying to probe this sweet spot are not super sufficient because most of these experiments focusing on 1 photon frequency to search for, and therefore trying to make a wide net search is not super. It's very difficult to speak. So there's still a lot of room for discovery. And disregard that, there's also these empty spaces. If dark matter doesn't, if axion-like particle don't solve strong CP, but they solve dark matter problem. In fact, you should be searching everywhere here. Okay, so there's still a lot of space for the younger generation to go after too. All right, so there are 3. Okay, so you can try to look for if the I'm almost. So you could look for such a particle One, Axion is really becoming part of the halo. So they are here, they are in the room, and they have this tiny probability of interacting with the photon field. You could also looking for the fact that they could be produced in some hot environments. For example, in the core of the sun, there's a lot of EM field creating these particles, and they beam to us, and we detect them. So this is called a helioskop, solar axion. And then you could also try to produce with the strong laser field, a strong EM field, producing them and trying to detect them. This is called light shining through the wall. So the helioskop people are using a resonator, trying to create the halo dark matter, converting into a visible electromagnetic signal in the lab. And the helioscope, looking at the sun, is really pointing your telescope to the sun and watching for the keV energy, okay? Because these axions were created really by the temperature of the sun. They are also, although light, they could be massless, so very light, but they're keV kinetic energy axions being converted into keV like X-rays in a strong magnetic field. Okay, so that's project such as IAXO in Europe is one of the leading sort of flagship experiment in the next generation. And then you can try to do it in the lab. It's more complex because in the lab you have a strong laser field, you create these axions, you cannot see them. You cannot really count the laser beam, one by one photon. It's also hard because the strong lasers are intrinsically very, very dirty. So people normally do is to put a wall, quote unquote, put a big barrier so nothing can go through except the axion. And then on the other side, you put another strong magnetic field to reconvert the axion back into photon. And that seems to be an efficient way of doing that, but people are still doing. It's difficult because the coupling constant of the axion gets multiplied twice. In this case, you need both conversion and the regeneration this way. All right. So so there's a big experiment called ALPS-2 at the DAISY working this. I'm ending, but I'm only talking to you about two sort of viable, theoretically motivated models. And now theorists are laying down. There's a term in China called laying down, meaning that, anything is possible, you just go search. They're not providing us with guidance anymore, Also, unlike 15 years ago, they said go search in this region. And nowadays, the theorists are saying anywhere is good, which frustrates me because, all of a sudden you're losing confidence of, whether you're doing the right thing. Anyway, it's a whole landscape. It's probably now at the extreme condition, that's probably also not super optimal, but that's the way it is. So all the way from what we discussed, a primordial black hole, to these wavy-like axion particles, everything is possible. But it also opens up a lot of possibilities. Okay, so yeah. So before I end, I just want to also put our propaganda for the fancy Centaur Lee PhD student program as a PhD program. So we encourage, we have a lot of domestic students, but we like students from international to join us a journey. So it's a 5-year program. You get very well paid, better than other students. So it's an elite program that we managed to get from our ministry. So thank you very much.
Thank you, Jianglai. So it was very instructive. So please, questions.
Going over it.
You try to find the dark matter with assumptions that there is some additional interaction to usual gravitation, but there is, what can say about the possibility to detect the dark matter in assumptions that there are no such interaction. It seems that what do you think about the following way when you show the dark matter galore around galactic? Such galore should be make an effect when you use the gravitational lighting.
gravitational lensing.
When?
Sure.
What do you say?
Yes.
about this?
So a lot of the, maybe I'll use this. So a lot of the evidence that we call astrophysical evidence of dark matter, a lot of them were produced by the lensing. For example, if there's a very massive galaxy containing a lot of dark matter, and then you see the galaxy behind it, by using the lensing, they were able to measure actually the distribution of the mass in that galaxy. So such a technique has been used in all astrophysical data analysis. So what I mentioned, using CMB, using the large structure formation, using the lensing, all combined.
But you can calculate
Correct.
from the visible matter
Yes.
And compare it with the
Sure. And
what you see.
yes, that's being done, and that's part of the info that went into that pie chart of dark energy and dark matter concentration in the universe. So that has been a predominating evidence that have been used. The problem is that we have no idea what is the particle content of dark matter with only the astrophysical observation. So the question is, do we know dark matter is there? The question is not how much of dark matter is made up the universe. That's not the question. The question we are going after is, what is the elementary particle nature of dark matter? And that, it could be that this matter just happened to be not interacting with known particle. But then we still don't know what this particle is. There's no single particle that we know that only interact gravitationally. So that's the question. It's rather than an assumption, that's precisely the question we are going after. Yes.
Further questions, please? Students, come on, don't be shy. Yeah.
Thank you very much for the
Yes.
speech. The one is, what processes in the sun can lead to the generation of KV axions?
Simplistically, it's just inside the sun, there's a lot of strong electromagnetic field. So if there is a coupling of the axion with the photon, then it's inevitable that it's being produced inside the sun. And the environmental temperature just makes the characteristic energy scale of the solar axion about keV-ish. Yes.
They are thermally generated.
They are, say it again?
Thermally generated.
Well, thermally generated meaning that it's EM wave, right? It's electromagnetic field or electrons. They're generating it through fundamental interaction. But yes, you can normally say it's thermally generated because they are interacting with the environment.
Okay.
Yes.
Further questions, please? I've got a somewhat provocative question. So,
Yes.
when we're searching for axions, for instance, and we're making these artificial resonators, or we're producing the huge magnetic field, so is it more efficient to search for some natural environment like neutron stars, for instance, where the
Of course.
huge magnetic fields are we get?
Yes. Yes. So people are doing that. Do I have a plot? You see a lot of these boundaries are produced really by these astrophysical glob cluster. Yeah. So it's really a complementary aspect. A lot of people are doing it in the laboratory. I'm focusing on the laboratory research. But certainly there's tons of papers produced by people looking at these very extreme astrophysical environment and looking for whether you see something or not. And they should be taken seriously. I agree with you. Yes, sure.
Okay, time for the last question.
No students. Yeah, I have a question regarding these force carriers, hypothetical force carriers. So the first argument which comes to my mind is that dark matter, in order to be localized in a galaxy, it should be able somehow to release its energy in order to get gravitationally bound. At the very beginning, when galaxies begin to be formed, so in order to have a negative energy, you have to release energy somehow. this is true for any other particles, not only for dark matter.
Right.
And the only option which comes to my mind is the kind of natural one. That they should be coupled to photons, because this way they can release photons, the energy in forms of the photons, and then become gravitationally bound to the gas. So I think this is one of the directions where to search. And so probably in this regard, Axions is a really promising candidate. But on the other hand, what I'm thinking is that in particle physics, we have carefully measured lots of cross-sections, including processes with some interference of carriers, like E plus E minus to fermion, antifermion via Z or gamma.
Yes.
And if you have some extra force, then you should be able to see this right away
Yes.
in the cross sections. So and we have lots of data like that. So I think all possible carriers with their masses and so on should be at first place searched, maybe reanalyzed the existing data.
No, I believe this has been done at the LHC. You know, it's Z prime, for example, is a popular things, and you can always cast their limit into a dark matter cross-section limit.
Yes, so
and this has been done.
In this way, we...
I don't know whether it's systematic, but this has such a practice.
In this way, we kind of rule out all additional
Possible indirect.
force carriers, right?
Yes.
And if it is so, then we are left more or less with the standard force carriers.
Yeah.
Yes,
well, one thing I'm not super sure is that when you do the Z prime analysis, you could still assume that the coupling constant at both vertices, you could still tune it. So they can cast it in terms of something. You can always tune it down to await the thing, unless you assume it's order 1.
Yeah.
Yeah. I mean, Z prime could, Z prime doesn't have to be coupled to neutron. For example, quarks and quarks with the order 1 coupling. So anyway, but you're right. I think that for any carriers that's searched, you could always assume it's a dark carrier and come up with at least some constraint to the scattering cross section.
Yeah, and one more question, not related to this. At the very first slide, you mentioned this exclusion plots, where we also have some kind of discovery plot from Gamma and Cogent. So can you comment on this?
Yeah.
You didn't say anything about
Very quickly. So Dama was a standout anomaly for years. When all these more and more sensitive detectors are ruling out the parameter space, they're ruling it out, assuming the fact that every nucleus, no matter whether you're talking about iodine or all these versus xenon versus anything, dark matter choose to interact with proton and neutron in the same way. Now you could imagine that there's some funny cancellation, that the amplitude of the proton and neutron is just such that they cancel somehow, so you don't produce a signal in xenon and you produce a signal in that. So people play with that for the first few years, and then eventually the xenon limits just get too deep that this playing with the coupling constant between proton and neutron do not work. And I should say that eventually, I think that the more competitive reason of sort of discredit or at least challenging the Dama data was because there are later measurements using identical sodium iodide detector. In the past few years, by the way, they produce data. And the current stage is that in combination of 2 experiments, one in Korea, one in Spain, that rule out the Dama annual modulation signal in a model independent way for sigma. That's the stage now.
Okay.
Yes.
Thank you.
Yes.
Okay, we need to proceed. So let's thank Jianglai again.
Thank you.